Alright, this is the video presentation of the modeling airflow interference in biplane wings. I am Patrick Kruger, and I will walk you through this presentation. So let's define the terms right off the bat. The angle of incidence is the angle of the wing mounting in relation to the fuselage's longitudinal axis. This is, in essence, saying the angle of your wing to the nose. Alpha is the engineering term for angle of attack. In the angle of attack is the angle of the chord line to the relative wind. This dictates your stall characteristics and how much lift and drag your aircraft generates. Stalling is the phenomena that occurs past the critical angle of attack, where the airflow separates from the top and the bottom of the wing. This results in a loss of lift and a loss of controllability of the aircraft. You lose a lot of options when your plane is stalling. And this is shown down there in the diagram in that picture. This shows what stalling looks like and how it happens. Decollage is the difference in angle of incidence of the different wings in a biplane. So if you have two separate wings, you can have different angles of incidence, right? Theoretically. And in fact, most biplanes actually do express show a little bit of decollage in the design. The problem that we're trying to solve is based on our senior design problem, based on our senior design project. That is, we have the bottom wing and the top wing, and what we're trying to do is we're trying to figure out, okay, is there a problem when the plane starts flying at high angles of attack, like at low speeds? Is there a problem where the bottom wing will interfere with the top wing? So we're trying to solve this issue, and we're trying to simulate it through CFD to see if this is going to become a problem, as well as if controlling the decollage could be an easiest solution to just make sure that it doesn't actually get into that sort of flight dynamic. So it just keeps you out of that flight parameter. So our proposed solution is to create a differential angle of incidence that will permanently cause the front wing to stall before the rear. That this, in essence, is saying that because the front wing will stall before the rear wing will push up on the plane, therefore pushing the nose down. And then this will just automatically correct the stall. There's lots of planes that have this express behavior built into them to make them safer and more benign to fly. So we're going to test this in ANSYS Fluent. So I tested the viability of the solution by setting up a simulation similar to the rotating airfoil assignment that we did for the CFD class. But instead of one airfoil, we have two airfoils that are mounted at different angles, the top one being mounted 3 degrees down to the bottom wing based on some cursory research I did. This is about accurate for decollage. So we imported the coordinates from that I got off of a website that generates coordinate files for different airfoils. I used the pattern to create the second airfoil instead of trying to import the coordinates a second time because they don't actually do it like this. And I rotated that top airfoil 3 degrees around the z-axis. You create a rotate circle, and I created the fluid geometry. And after that, we go on to the meshing. So to mesh, we set all triangles on both geometries. So you set the whole entire thing to all triangles. You set body sizings to fluid and rotate both those. So you set the body sizings to the fluid and the rotate, because the fluid is the outer D-shaped thing and the rotate is the circle. You set the body sizings on those to 0.02 and the edge sizings to 0.01. Now, and then you use the refinement on fluid and rotate to 2. And this will end up, if you do this properly, you'll have a meshing that looks very similar to that. You then name the sections appropriately, and then you can move on to the simulation phase. This is the very important part. And this is the part that we messed up on when we did this the first time. So you use the K-epsilon model. This is what you have to use for turbulent modeling. It works very well for this exact kind of sort of simulation. So you use K epsilon and you rotate it around the midpoint of the circle. This is the thing that we messed up on when we did this. I did not rotate it around midpoint. I was accidentally rotating it around 0, 0 and not correcting it. And then for me, and the velocity magnitude, I took on the inlet, which is the front name section, the round part of the D. I took that and I set the velocity magnitude to 10 meters per second straight toward the airfoil. You initialize it using hybrid initialization, and then you set up the animations appropriately. Okay, so I'll have the links to these videos in the description. I've already uploaded them onto this channel, and if you look at it, you'll be able to easily see what I'm trying to show you, and then you'll be able to understand what I'm talking about when what we just saw and what conclusions I drew. So what we just saw was, you can see once on both the velocity and the pressure animation, there's a certain angle of attack that once you get to, the front wing starts getting in the way of the rear wing's airflow. That breaks it up and that causes a problem. But if you are noticing, if you look at the pressure diagram, before that happens, the pressure difference on the front wing starts dropping, and this dropping in pressure indicates that there's a stall and the wing is not flying anymore. This means that it does technically autocorrect. Now, our final conclusions are decollage has a utility for sure. It can definitely keep you out of these dangerous flying conditions. So different wing configurations affect on safety. Yeah, especially now that I've actually tried out the different one, where the front wing is on the top instead of the bottom. It's substantially safer. It has a lot more options when you're trying to fly it. And do we need any changes needed in the wing configuration? I would say so, especially after trying a different one. The different one is definitely better. The conventional biplane setup is substantially safer. So I think that our team is moving more in that direction, and we will see where that leads us. If you have any questions, just leave them in the comments below, and I will try to get back to you as best I can. Thank you for watching the video, and you guys all have a good day.